A linear operator T is self-adjoint when T equals its adjoint T star. Many authors call this Hermitian. Same mathematical animal, just wearing a fancier name tag. The guiding analogy is complex conjugation. A number is real exactly when it equals its conjugate. Self-adjoint operators are the operator version of that idea. First fact: every eigenvalue of a self-adjoint operator is real. In the complex case, this is where the operator stops pretending it has exotic eigenvalues. The calculation is just the adjoint definition and conjugate linearity in the second slot. Since V is non-zero, its squared length is positive, so lambda equals its conjugate. So the eigenvalue is real, a rare moment where the symbols behave politely. Now a complex-only tool. If the diagonal expression angle bracket TV, V is always 0, then T itself is 0. The point is this polarization identity. The right side only uses terms of the form angle bracket TX. X. Yes, the formula looks manufactured. That is because it is doing exactly the job we need. If all diagonal terms vanish, then the identity gives angle bracket TU. W equals 0 for every U and W. Taking W equals TU gives TU equals 0. For complex inner product spaces, T is self-adjoint exactly when angle bracket TV. V is real for every V. One direction is immediate. If T equals T star, then angle bracket TV, V equals its own conjugate, so it is real. For the converse, apply the previous result to T minus T star. Its diagonal expression is 0. So T minus T star is the 0 operator. Astonishingly, a useful result got reused instead of being abandoned like gym equipment in February. Next, if T is self-adjoint and angle bracket TV, V is always 0, then T is 0. In complex spaces this already follows from the previous complex result. For real spaces, the complex polarization identity is not available, so self-adjointness is exactly what makes the real version work. The first equality uses self-adjointness, and the second uses real symmetry. Then the same final trick applies. Choose W equals TU, and the operator collapses to 0. Next time we define normal operators. Operators that commute with their adjoints. Every self-adjoint operator is normal, but normal operators are a much bigger universe. Naturally, the universe needed more cases.